Hey everybody, back for another video lecture here. Today we're working on Chapter 4, Section 3, which is the fundamental theorem of calculus. And what the fundamental theorem of calculus will do for us is it's going to make it a lot easier to calculate definite integrals, like we see here in the first example, by just evaluating the antiderivative. So we're going to do the first example here, and then I'm going to explain how this fits into a little bit bigger picture. So the way that you're going to calculate definite integrals using the fundamental theorem of calculus, which is going to be the main way that you're going to calculate integrals from now on, is that you're going to calculate the antiderivative. So the antiderivative of t squared is t cubed over 3, and the antiderivative of 4 is 4t. And then we're going to use this notation. We're going to evaluate this antiderivative from 0 to 3, which means that we're going to plug in 3, and we're going to plug in 0 into the antiderivative. We're going to calculate the difference of those. So when we plug in a 3, we get 3 cubed over 3 minus 4 times 3. That's our antiderivative evaluated at 3. And then we're going to go ahead and plug a 0 in there, and we get 0 minus 0. So our overall derivative, then, or our overall integral then, is 27 over 3 minus 12, or 9 minus 12, which is negative 3. So let's scroll over here and just do a quick minute to explain how everything fits together. So the last 3 sections all had to do with finding the area under a curve. And what we did in section 4.1, which was the Riemann sum section, is that we figured out how to approximate the area using a finite number of rectangles. But what we want to do is we want to calculate the exact area underneath the curve. And there's 3 ways that we can calculate the exact area. The first and the easiest way is to use geometry. Unfortunately, we can only do this with things that are made up of a collection of rectangles, circles, and triangles, because those are the shapes that we know the areas for. So we can only do this on a certain number of problems. This only works for, we'll call it, nice areas that include these 3 kinds of shapes. And what we did in section 4.2 is we can use an infinite number of rectangles in a Riemann sum. And as you remember from section 4.2, this is very hard because it involves calculating an infinite limit of a Riemann sum, where we're doing this weird function evaluated at the right-hand endpoints times delta x, and this just ends up being a really nasty series calculation. And so far we can actually only do this for things that are up to squared functions, because we only have the series summation formulas for 1, I, and I squared. So this will work for all functions, but we only really know how to do it for really basic functions. The third and most powerful way to find the area under a curve is by using the fundamental theorem of calculus. And what the fundamental theorem tells us is that the integral from a to b of f of x dx, so the area under the curve f of x from a to b, is exactly equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So it kind of gets completely around all of this Riemann sum stuff, and we can just kind of magically use the antiderivative to calculate those areas. And that's what we're going to be doing for the rest of this lesson. So we already did that in our first example here. We calculated the antiderivative and we plugged in 3 and we plugged in 0 and found the difference between those two, and that gave us the area underneath our curve. Let's go ahead and do that for example B and example C. So for example B, first we're going to need to rewrite this problem in a form that we can find the antiderivative of, because we can't find antiderivatives of rational functions right now because we don't know how to undo the quotient rule. So if we go ahead and split up that fraction, we can then simplify each of the independent terms. So we get 1 over square root u minus 2u du. And I'm going to go ahead and rewrite those in power function notation so that we can find the antiderivative a little bit more easily. So we get u to the negative 1/2 minus 2u du. Now when we find the antiderivative, we're going to go u to the 1/2 divided by 1/2 minus u squared. And then I'm going to, now that I've calculated the integral, so here I had my integrand, and after I found the antiderivative, I need to change my notation to show that we're evaluating this antiderivative from 0 to 9. We've already taken the antiderivative, so I have to drop this integration symbol. Now I can go ahead and plug this in. I'm going to go ahead and simplify this. This is 2 square root of u right here. So then I get 2 square root of 9 minus 9 squared minus 2 times square root of 0 minus 0 squared. And if I simplify that one step, I have 2 times 3 minus 81. That whole term over there is 0. So I get 6 minus 81, which is negative 75, as my answer for part B. Let's keep this train rolling, and let's do the exact same thing here for part C. The trick to part C is that we're dealing with an absolute value function. So I'm going to go ahead and graph here the t squared minus 4. And then I need to note that when we do the absolute value of t squared minus 4, we're going to flip this negative part. So I'm actually going to need to use piecewise function. So this is negative t squared minus 4 from 0 to 2. And it is t squared minus 4 from 2 to 3. So I am going to be finding two different areas, area 1 here and area 2 here, by using a sum of integrals. So I'm going to be doing the integral from 0 to 2 of negative t squared minus 4 dt, and then the integral from 2 to 3 of positive t squared minus 4 dt. I can just pull out that negative right here. So I have 0 to 2, t squared minus 4 dt, and then the integral from 2 to 3, t squared minus 4 dt. Now remember, I pulled out this negative right here because that has to do with our absolute value function. So the antiderivative is t cubed over 3 minus 4t, and we're going to evaluate that from 0 to 4. Notice here I use these big square brackets on the outside to say that the inside of this is being evaluated from 0 to 2, not 0 to 4. We have our negative out front here. And then we are going to evaluate the antiderivative here, t cubed over 3 minus 4. We're going to go ahead and plug in a 2 and a 3 for t. Sorry. We're going to go ahead and plug a 2 and a 3 into that. So let's go and evaluate this. So when we plug in a 2 here, we get 8/3 minus 8 minus, then when we plug in a 0 there, we get a 0. And now over here, when we plug in a 3, we get 27/3 minus 12 minus 8/3 minus 8. Let's go ahead and end our parenthesis here and end our big square bracket. So then what we have is we have negative 8/3 plus 8 plus 27 thirds minus 12 minus 8 thirds plus 8. And so I have 16 minus 12 is 4. And then 27 minus 16 thirds is 11 thirds. And so 4 plus 11 thirds is our total area underneath the curve of the absolute value of t squared minus 4. I'm going to give you a second to jot down that work here. All right, let's move on to our next example. So example 14 here is like web work 4.3 number 7. So why don't you go ahead and try to work this out before I show you the example. I'm going to give you 5 seconds to pause and then go ahead and play it when you want to see me work out that solution. Alrighty, now that you've tried this on your own, what we need to do here is we need to calculate the antiderivative. I'm going to start by writing this as 8x to the negative 2 minus 6. So I know how to take the antiderivative a little bit better. So I'm going to go 8x to the negative 1 divided by negative 1 minus 6x evaluated from negative 8 to negative 3. That's like negative 8 over x minus 6x evaluated from negative 8 to negative 3. Oops, I used the wrong bracket there. This should be a straight line if we just use one of them. If we close it in on the left and the right, we can use the bracket. Okay, so now let's go ahead and plug in our negative 3. So we have negative 8 over negative 3 minus 6 times negative 3. And then we're going to subtract our antiderivative evaluated at our a value, which is negative 8. So we get negative 8 over negative 8 minus 6 times negative 8. And if we simplify these things a little bit, we get 8 thirds plus 18 minus 1 minus 48. And so we end up then with 8 thirds minus 31 as our integral for this problem. Alrighty, so that's pretty straightforward. Now, for example 15, we have a different kind of problem altogether. What we're doing for both part A and part B is we're finding the derivative of a function where the function is an integral. Alright, so let's do some work to the side here really quickly. So if we have some function in here, and we're finding the derivative from a to b of that function, we get the antiderivative evaluated at b minus the antiderivative evaluated at a. This is the fundamental theorem of calculus, this equality right here. So now, let's say that we took the derivative of both sides. So we're taking the derivative of this integral. Okay, we're going to take that derivative. And then we're taking the derivative of these antiderivatives. So if we're finding the derivative of an integral, this is the question that we're being asked. Okay. And the answer should be, what's the derivative of the antiderivative? Well, it must be the original function evaluated at b, and then we need to do a chain rule, and we need to multiply it by b prime minus the original function evaluated at a times a prime. Okay, so we're taking the original function that we are finding the integral of, and if we're going to take the derivative of that integral, we end up with that original function evaluated at the endpoints multiplied by the derivative of the endpoints. So how does that work out for example A? Okay, so what we're going to do here is we're going to plug in the upper bound, and then we're going to multiply by the derivative of the upper bound, which in this case is 1. So we're taking the derivative of 1, which is 0. And then for the lower one, we're going to go ahead and plug in that lower bound. So we get 1 minus x squared, and that is supposed to be an x because the lower bound is x. And we're plugging that in to this t function right here. And then we're going to divide that by 1 plus x, x to the fourth. And now what we need to do is we need to multiply by 1 because that is the derivative of our x bound. And so our answer here is just negative, which is that negative, 1 minus x squared over 1 plus x to the fourth times 1, which we don't need to write. So this looks remarkably similar to the integrand right here. We have the negative because this is the lower bound here where we're plugging in our x, so we get a negative. If this was the integral from 0 to x, let's say, with x in the upper bound, we would have got our non-zero term to be first, and this would have been a positive number. For now, the answer here is just negative 1 minus x squared over 1 plus x to the fourth. Let's do the exact same thing for example B. So what we're going to do for example B is we're going to plug in our upper bound, which is x squared for the t there, and then we're going to plug in that x squared into the into the t in the denominator as well, and then we need to multiply by 2x because that is the derivative of that x squared. And then we need to subtract off cosine of 3 over 1 plus 3 to the fifth times 0 because the derivative of 3 is 0. You could have just seen that we're not going to have the minus term at all because we have a constant here in the denominator. So overall, our answer here is cosine of x squared divided by 1 plus x to the 10th, just a little bit of simplification there. And then we could have put that 2x out front of the cosine when we have this 2x that we're multiplying. Or we can just leave that 2x where it was. We're multiplying this whole thing by 2x, and this will work for your final answer of the derivative of capital F prime of x, where capital F is an integral. So the derivative of an integral is very similar to the integrand because derivatives and integrals are inverse functions of each other. We just have to make sure that we multiply by the derivative of the bound to deal with the chain rule. So I'm going to go ahead and leave that up for 5 seconds here so you can copy any of those notes. Guess we could also say that this is like more of the notes about how we're doing those problems. This isn't any part of the solution. All right, let's move on to the next examples here. So example 16, we're doing the exact same thing we did in the last two examples, but now we have a variable in both the upper and the lower bounds. So what we're going to do here is we're going to do that j prime of x, so the derivative of the integral, is just the sine of 3x plus 1 to the fourth times 3. So what I did is I plugged in the upper bound in for that t, and then we needed to multiply by the derivative of 3x plus 1, which is that 3. And then I need to subtract. We're going to plug in the lower bound now. So the sine of 2x to the fourth times 2, because 2 is the derivative of 2x. So this is like f of b times b prime minus f of a times a prime. And so our final answer here is just 3 sine of 3x plus 1 to the fourth power minus 2 sine of 2x to the fourth power. And that's all we do. Alrighty. Last example here. This is a web work problem number 11. And then we'll be done with our 4.3 notes. Like I've been saying, 4.3 is kind of the magical math formulas that let us figure out these areas by using antiderivatives. And this section should be a little bit easier because it's just tying together the area under the curve to our antiderivative stuff. So all we're going to do here, f prime of x, is going to be 5 sine squared of x squared times 2x. Again, this is our derivative of our x squared, minus 5 sine squared of x times 1, because that is our derivative of x. And so our final answer here, just one step simplified, is 10x sine squared of x squared minus 5 sine squared of x. And that's it for your 4.3 notes.